Okay, can you see the slide in the screen? Anyone? Hello? Can anyone see? Is it possible to see the screen, sir? Madam, anyone? Okay, good. Uh, Now we'll start the lecture again as where we stopped last time. So we actually been talking about chemical bonding, and then we started with the shapes, and we discussed about chemical bond in a detailed way. And here in a generic, if you see the periodic table, you will see different segments of the periodic table. In that one segment is they were trying to segregate into three different types. That is 1, 2, 3 electrons on the outer shell, and 5, 6, 7 electrons on the outer shell, and 4 electrons in the outer shell. But it's always that 1, 2, 3 electrons want to lose its electron to actually attain a stable condition. Similarly, 5, 6, 7 want to gain electrons to actually be at a stable configuration, like the inert gases. So they were actually 1, 2, 3 will lose to 5, 6, 7. Similarly, 5, 6, 7 will try to gain from 1, 2 electrons from the outer shell. Okay? This is what generic it is happening in the nature. And the 4 electron in the outer shell will always try to get combinated with the 4 electrons only, mostly. So the other than 4 electrons is possible, but still this is more common that you see in the general, the natural phenomenon. So with this, the carbon is at the 4 electron in the outer shell, and it trying to combine with the carbon. That's why the carbon-carbon bonds are quite attached. This is the one reason here. And next we come into shapes, as we already talked S, P, D, S, F, shapes. And also we actually discussed about K, L, M, N as shells, okay? And depending on the energy level, they distinguish the K, L, M, N shell types, and depending on the shape, they will talk about the S, P, D, F. And once we are coming into the shape, as I said, S, P, D, F, and you see the first one is a spherical, and the next one is a tumble shape, and the D is also almost like a long, elongated type, and to this parallel, they were actually called the nodal plane. Okay, to the parallel to the electron, it is called the nodal plane. That is what. So the nodal plane is actually represented as a tumble. So this is quite common, and if you see the F, it is more complicated. If you see D itself, it's too complicated to see. This is in the 3D, and mostly they want to represent in 2D. That's why they put it there with the arrow mark. Okay, that they want to show in a 2D diagram. Next, we've been talking about chemical bonding in distinguished with I mean the different chemical bonding. Ionic, covalent are the most often used uh, chemical bonding in our chemistry in our subject, and ionic is it's more in the crystals, so we don't talk much, and we talk more on the covalent. That's going to be that will actually be involved in the reaction mechanism often. And in that sigma bonding, pi bonding are the important bonding natures. So depending on the bonding size, they will actually represent as sp, sp1, 2, sp3 hybridized and stuffs like that in the form of structure. The sp, it is very simple that you talk about one s and mostly one p. S orbital means if you see in the valency bond orbital where the s bonds get attached. Okay, so the s bonds get attached, then it's s. And with this s, there will be p bond. If s and p bond attached to the same group or something related to the same like element, then it's called a sp. And if you get pi bond involved in that, then it's sp2. If you have a triple bond, that is unsaturated, if it's three bonds involved in the same group, then it's a sp3. That is why sp, sp2, sp3s are quite common in carbon. Okay. There is no sp4, only sp3. They will talk about the bonding nature. Okay. So depending on its binding energy, you see the energy level is very high for sp3 because it is a three unsaturated bonds. That means the two atoms are very close enough. That is, it quite have much higher potential energy. The high potential energy hold the two atoms in a very close to each other. It's sp3. And the least one is sp. Sp is only single bonding between the p and the p. So the energy level will be low. So it is always need higher energy to saturate sp3, and then it comes sp2, and then it comes to sp. That means from sp3 to sp2, it actually needs some energy to saturate. But I don't say the reactivity is very slow here. The reactivity is really high. If sp3 has to convert into sp2 form, it is more reactive. And if it's sp2 is more reactive than sp. So this is how it's been distinguished. So if you see that, we actually talk about sp2 and sp3 much in our reaction mechanisms. Okay, we'll just talk on the next one on this. Once we're talking about the covalent bond, we see two theories. One is valency bond theory and another is the molecular theory. Valency bond theory only talks about the individual atom connection in an atomic orbit. Individual atom within a molecule get connected by the atomic orbit. That is one electron orbit connected to the another electron orbit. But in the molecular orbit theory, it actually gives an overall or a total energy which gains and loses by the bonding. So it does not say about the individuality, it says about the overall. Okay, that's what we've been discussing, and I just explained about how the bondings happen and how it's been represented. And you see the sigma bonds are quite often been mentioned in the valency bond theory. SS overlap, SP overlap, and PZ overlap. Uh, there is a four valency in carbon. They will divide in a one S, one PX, one PY, one PZ. So the all these four orbital require four electrons to get saturated. Okay, because these all are in a pair. That is how the sigma bonding will be there. And similarly, if you try to put it in a like energy level, this is the energy level. This actually goes up. So the energy level is high here. This is high energy and this is low energy. This is, the bonding is anti-bonding. So when compared to sigma bond, pi bond looks somewhat different, and the energy level, if you sum it up, will be somewhat lesser than compared to sigma bond, because the sigma bond have higher energy to get bind. That is the first bond to get bind in a reaction, and the next one will be your pi bond will start to get bind in your molecules. Okay, that is why we actually show in such a way. And if you see anti-bonding and the bonding is the one which try to attract each other, and the anti-bonding will says about how it try to repel like each other. Okay, so if you see the electron and the nucleus, it try to attract each other. So the electron of one atom and the nucleus of the other atom try to get attached. So this bonding is the more stable sigma bonding. And the electron on the outer side of one particular atom and the electron on the other side of the atom try to repel each other. That is called the anti-bonding. So these two has to be summed up to see the actual energy need. Okay. So they actually talk much in this Morris diagram, Morris plot. There is a Morris plot and things like that. There is so many things in the physics. They will try to represent how the energy levels between two atoms, if it start to come closer and closer. So that is what we need to look on. Okay, so that is being applied here. And if you see the representations, that this is the sigma bond, that is the thumb shape is actually overlapping each other, and the pi bond is the one that actually get connected in the middle. That is how it's been represented. And this is the anti-bonding, and this is the bonding. You see, the electron will be on the opposite side, and the nucleus will be try to attract to the electron of the other atom. So this is sorry. So if you see that the bonding, it is trying to attract the nucleus. That is what I'm bonding. But here it gets repelled, and it's an anti-bonding. You see the diagram here. That's how it looks in the bonding and anti-bonding. Okay. And in general, I like to give the command is that greater the overlap, greater the stability of the bond. Okay, if you see the sigma and pi orbitals. So higher it gets, or very closer it gets overlapping, then it's a greater instability of the bond. When the center of electron density are on the axis common to the nuclei, or the overlapping is coaxial, the orbital is known as sigma orbital. Okay, so this is another definition about the sigma orbital, and this is actually been yeah. Yeah, here it has been represented quite nice. I, yes. If you see here, this is the pi bond or the sigma bond, and this is the pi bond. The sigma bond is the connection of S and P, and it get connected. And you see the nucleus and the electron get connected here. And here the nucleus is at the middle, but the electron is trying to repel. So that is what it's the difference here. That is how they will try to represent it. And when the center of electron density are on the axis common to the nucleus or the overlap is coexisted. If it get overlap and it, okay, then it's called a bonding, sigma bonding. Okay. But if you see the pi bond, sideways overlapping. So the side, the tumble side will try to get overlap with the closest like atom. So this sideway represent, I mean, the overlap of the tumbles will be represented as the pi bond. By sideways overlapping, having only one nodal plane along the nuclear axis, which is only one nodal plane. You see, this is the nucleus and this is the nucleus, and you have only one plane. So this is the plane. Similarly here, for bonding and anti-bonding, you see there is only one nodal plane. But the tumbles will be connected for bonding, and it will be repelling for the anti-bonding. This is the representation of pi bonding. Similarly, for sigma bonding, it is on the other side. Anti-bonding will try to repel with the electron to each other, and the coaxis will be at the middle. And for the bonding, it will try to attract each other. Okay. So this representation has to be mainly described in sigma and pi bonding. These two are major bonding in our carbon to carbon. Okay. So if you see the comparison or differences between the two theories, the valency bond theory begins with two steps. One is hybridization, and another is the combination. Hybridization is nothing but atomic orbits. AO represents the atomic orbits. The atomic orbits on atom participating in bonding. That is the only thing. So the atomic orbits will participate here. And the combination of hybrid orbits to make bonds. You see there is difference. The atomic bond will start to participate first, and the hybrid orbit will try to combine together and form a very strong bond. Okay. So now we see the difference between the valency bond and the molecular orbital bond. The first one is that electron distributed over whole molecules. That is the molecule center. That means the whole molecule will be calculated. So the energy level of the whole molecules will be calculated together in a molecular orbital theory. But in valency bond theory, a localized pair of electrons, that is two atoms, will try to bind by the pair of electrons. So one electron of one component and the other electron on the other atom will try to get bind. So you will see individual electrons and how it's been connected to each other. The next one, molecular orbital theory combines atomic orbital between different atoms to make molecular orbits. So the molecular orbits will have different atoms. So The valency bond combines atomic orbital of the same atom. So what it means that the same atom connections been more elaborately explained by the valency bond theory. Different atoms or different atoms. I mean, for example, you have carbon and hydrogen bonding. That is more described in your molecular orbital theory. But in valency bond theory, they more talk about the carbon to carbon. Okay, so this is one difference. And another one, molecular weight theory have symmetric must be retained in each orbital. But valency bond theory, all orbital must be viewed simultaneously to see retention of the molecule. Symmetric. So this is what I said again. You see in the molecular orbit theory combined everything all together. So you say the particular atom to atom connection will be in a symmetric. There is no deviation. But in the valency bond, you will see simultaneously each and every orbit separately. Like the atomic orbit, everything will be segregated different. But why this happens? If you take an example of the infrared spectroscopy, they try to identify the different molecules and its shape. So there, the molecules and its binding nature will be identified by using the vibration theory. So how the vibration or how the bending and how the stretching is happened once you put some extra energy on the material, on the molecule. Sometimes it may tumble each other, or sometimes it may repel each other, sometimes it may vibrate heavily between each other, sometimes it may uh, elasticate within two molecules. So the bond will get elastic. It is like a rubber, or it's like a tape or something, elastic tape. So something it will be happen, and these type of things will give the result of which type of atom it is and which type of molecule it is. That is how they were identifying the molecules in spectroscopy. Okay. That is a very important concept they use to identify the spectroscopy. This comes from this particular theory, what they were been trying to understand in the previous stages. Okay. So this is what the end of this particular part. And I just stop for today because why is that this is one particular topic that I want to stop. And the next topic is about the bond angle, and we are going to talk about bond length and the bond energy, and then the effect which creates in the bonding nature, and why there is a complication and why there is only particular atom actually combined with the other atom, what are the differences and how it's been acting as such things, and the mesomerism and the resonances all are in will be covered in the next few days. And once we cover this, then we finish basic chemistry, and then we go for the purification sections. That is totally a chemical engineering part. Okay? So I really appreciate if you have any queries. So I give you another 2-3 minutes for queries, then I will go for the admins. Okay, now I stop recording the particular lecture. Then I go with the uh, attendance, and I need to talk about a few things in very short. Uh, so I really appreciate if everybody holds the network. Don't forget. I just stop now.